Okay, so week 6, there is only one notebook with everything inside, so you can follow on your own computer. Text analytics. Okay, so yes, so as you saw during the class, text analytics is the process of deriving high quality information from text. So text can be anything, website, books, video, lyrics from music, reviews, articles, stuff like this. And here is the table of content. I will start with a short summary of some concepts that are important. Then we will go through text preparation, tokenization, dependency parsing, lemmatization, for instance. Then we will do text representation, how to prepare to turn text into numbers, to make a text, to prepare a text and make it ready for a classification algorithm, for instance. And then we will go through a real example where we will try to classify reviews from Alexa from Amazon. There is something in the chat. Where is it? Okay. So first of all, the summary. So there are many applications of text analytics. I have some examples here. For instance, using a search engine, if you search for relevant websites or articles. Also, and we will see this, we will classify reviews as positive or negative. So this is called sentiment analysis. Of course, Siri and Alexa are also using text analytics to work. And during my master, I did a project on the impact of news on financial markets. And I have an idea if you don't have any idea for the project, but I think the project is like you don't have to find an idea. I'm not sure, but if you have to find an idea, this would be a nice one. For instance, the impact of Donald Trump's tweets on the financial markets. This could be an idea. So there are many applications of text analytics. Second concept, basically two concepts, tokenization and stop words. Tokenization is the process of splitting a sentence into tokens, into words or characters. For instance, I love data science. I love data science, so you split it. And the stop words are the common words of the language you're analyzing. For example, in English, is, and, you, I, me, and so on. And it is convenient to remove them because they are present in all documents, and therefore they're generally not useful for the analysis. And they also can make the analysis worse because they are noise. So it's more efficient, and as we saw also, this is very useful to remove them because otherwise the bag of word, the matrix is the feature matrix is like very, very large, and this is not so convenient. So the next one is lemmatization and stemming. So the goal of it is to have the same token for different form of a word. The basic example I have is fishing, fished, fisher, and fishers. We want to have fish. And lemmatization is, the aim is to find the lemma of a word, and this goes beyond stemming, because stemming is only to remove the end, so the suffix. For example, fishing, fish, but lemmatization goes beyond this, because, for instance, it will change feet into foot, not only removing the end. So stemming is a type of lemmatization, and lemmatization is the goal of it is to have the same token for different word, a form of a word. Okay. And is there any question? Someone is talking. Okay, no. Okay, and finally, text representation. The goal of it, as I said earlier, is to transform a text such that it can be used for text analysis. So yes, you can easily imagine that you don't feed an algorithm with a raw text. So we have to transform it into numbers, because algorithm like numbers. So there are two main ways to do this: the bag of words and the TF-IDF, and I will explain them later on because we will do both of them with an example. So, but basically the aim of text representation is to turn a text into numbers such that it can be used to fit in an algorithm. Okay, any question on the first section? Okay. So let's go for the second part. Okay. So we will use, so in this section, we go through text preparation. This is how to prepare text for analysis. So this is not to turn it into numbers, but this is like tokenization, removing stop words, and so on and so forth. So we will use Spacy. Spacy, as it is written, this is an open source natural language processing library for Python. This is quite powerful. And we use this, and we also use the English language model of this library because we are analyzing English text. Okay, so the first step is to install it. Okay, so let's do this. And then, okay, so it's downloaded. I already have everything because I already installed this. Okay, and then we import it. We import Displacy. This is to show some beautiful plots of Spacy. We will see this later. Those two, count vectorizer and TF-IDF vectorizer, are for the bag of words, and the TF-ID vectorizer, yeah, and of course Panda as you, okay. Okay, tokenization. So tokenization, we have a sentence and we want to we have a sentence and we want to split it into tokens. So the the basic idea is to to split a sentence into words. So a token simply refers to an individual part of a sentence having some semantic values. So we can do this. Imagine you have this sentence. When learning data science, you shouldn't get discouraged. Challenges and setbacks aren't failure; they're just part of the journey. You've got this. So we have 3 sentences, and we want to split them into tokens, and we can use for instance word tokenization, where we split the sentences into each words. Okay, so we load the English language model, and then we create a document from the text with the English model, and then we can print it. So this yields, okay, space is not defined because I didn't import the packages, of course. Okay, and then I can do this. So we have our spacey object. This is a spacey document. So do not forget to do this step, because this makes a document from your text, and if you don't do this, this won't work. And for instance, we can do a list of token with this code. So we create a list for token in my doc. So for each word, we want a text, and this yields this results. And we can see two things. The first one is that each word is now so it's splitted the sentences into tokens, and tokens are in this case words, also punctuation, and also the return line. I don't know what it's called in English. And one important thing to notice is that, for instance, shouldn't it made 2 words of it. So this automatically recognized that shouldn't is actually should not, and the same for are not, and you've. So this is everything is automized. So, and we split the list into tokens. So each words, and also the punctuation marks, like the points. Okay. Any question on that? So basically, the step not to forget is to create a document from a spacey object, a spacey document from the text, such that it has all the, I will show this also later. For instance, we have, I will show this now because there is no question. The part of speech, this one. So we can also see the part of speech of each word. For instance, if it's an article, if it's a verb, if it's and so on and so forth. And I can show this, but what we can also do is, for instance, if you do something like word dot, because it's a spacey, because my doc is a spacey document, we have here everything related to this. So you can test if it's a number, if it's for instance, if it's a digit, if it's a lower, if it's a punctuation mark, if it's quotes, if it's a space, if it's a stop word, and so on and so forth. And this, we can use these methods, these attributes to. So there are lots. You can search for what you want. So because it's a spacey document, each words has those properties, and we will see a bit later what we can do. And one example of this is text, of course. So this we showed this just above. The text is only the text of the token, but also this part of speech. And this part of speech is like if it's an adverb, if it's a verb, if it's noun, and if it's a space, and so on and so forth. So this may be useful. Yes. And also, I have another example to illustrate this, because sometimes the word is a verb, like in I like fish, I like to fish. This is a verb, and sometimes the same words can be like a noun. And if you do this, it's automatically recognize in the first sentence that this is a verb, and in the second one that this is a noun. So this is it for this part of speech. Okay, and as I said, one way to tokenize is to split into words. And the second way to tokenize is to break the text into sentences. And to do this, we use from the MyDoc the attribute sense for sentence. And then we create a list of sentence where we add the text of the sentence in each in the list. And what it does, actually, it looks for as it's written here, it looks for specific characters that normally fall between sentences, like points, exclamation points, new line characters, stuff like this. So if we do this, we will end up with 3 sentences, the first one, the second one, and the third one. Okay. Any question on tokenization or part of speech? Okay. So it should be clear. It's not so difficult, I think. Okay, so dependency parsing. What is this? This gives, so we saw that we can see whether a word is a pronoun, a verb, a part, a particle, or a determinant, something like this. And what we can also see is like if the relations, the connections between the words. So, for instance, the sentence "Joe throws the ball." If we split this into tokens, we will have Joe throws the and ball. But we can, yeah, as it's written, we can't just look at this word individually, because we need like the connections, the relationships between the words. We have to make sure that it is Joe that throws the ball and not the ball that throws Joe. Yeah, and we have some way to do this with spaCy to look at the relationship between the the words. This is called like the chunk. And if we do this, we can see, for instance, that for the sentence Joe threw a ball and President Donald in pursuit of the ball hit a wall, we can see, for instance, that Joe is the subject of threw, ball is the object of threw, and President Donald is the subject of hit, and so on and so forth. And using display C, we can visualize this in a more beautiful way, and we see all connections between the words. For instance, we see, as I said before, that Joe is the subject of through, that is the determinant of ball, and through is the ball is the object of through, and so on and so forth. Okay, so this is a way to show this and to make sure that Joe threw the ball and not the ball threw Joe. Any question on dependency parsing? Okay.
There is a question in the chat.
Yeah, there is a question in the chat. I don't see it. Okay, do we have answers for the lab from the last week? I forgot to upload them. Thank you for writing me. I will upload them at the end of this session. Why did the input text have 3? Yes, this is a way to, because you can also do with 1 or with this. In Python, this doesn't make, so you mean this at the beginning. This, you mean this. Yes, in Python you can do either this one, those ones, and the 3. And if you do the 3, like if you have a quotation or something like this, for instance, he said double points. If you have a quotation with it, you can, for instance, it is easy. Do you see what I mean? So if you have the 3, you can have a quotation in your text, and if you have 2, this will like breaks your quotation. If I try it, and this won't work if you do like this. So if you do 3, you can do like some stuff like this shouldn't, and also you can have quotation within your so in your string. So I think it answered your question. Okay. Any questions? Any other questions? Okay. So stop words. Stop words are very common words in every documents, and we normally want to remove them because this can speed up the time on the analysis takes, for instance. But also this makes the algorithm more efficient because we don't this remove a bit of noise, because this makes a lot of noise if you have if you want to compare documents that have a lot of words that are the same. This makes noise, yeah. So we want to remove them normally, and we can have a look at the stop word spacey includes by default. So with this, so we load them, the stop words from spacey, and then we print the number of them, and the first 20. Let's do this. So by default, there are 326 stop words, and for instance, we have a last, which there, does, yourself, many. So all of those words are very frequent and therefore not so useful in many cases for the analysis. So we prefer to remove them in general. So now we can apply it to our document. So our 3 sentences. We want to remove the stop words. So for instance, I think when will be removed, you will be removed, maybe should not will be removed. And if we do this, so we use the is stop. So we create a list and we use the is stop for each word. If it's a stop word, we don't add it, and if it's not, we add it to the list. So that's what I meant with those attributes before. Like you have, and in the example below, we will also see other ones, but isTop is, for instance, one of those attributes, very useful. So if you do this, we see that, for instance, when has been removed, you should not get, so all words that appear very, very frequently. Okay, but we can also see that the punctuation has not been removed. So we can further do this. We can also remove the punctuation marks. So we remove the stop words, the punctuation, and also the spaces. So we create 2 lists, the one with the removed tokens and the second one with the filtered. So if we do this, if we run this, we end up with the removed tokens. So this is, for instance, the stop words, this is punctuation, and this is a space. And the filtered sentences are like this. So, and those words are now useful for the analysis to recognize the documents from which they come. Okay. Any question on this? Okay. So is it clear so far? No, nothing clear. So far, so good. Okay. So lemmatization. As I said earlier, the goal is to have only one token for different form of a word. For instance, connect, connection, connecting, connected. They have the same meaning, so we want to have the same token. There is a question, an interesting question in the chat. If we remove not when we filter, don't we lose the meaning of the sentence? Yes. That's a good point. We should, but I think we will see. You're right, but we will see how to handle this. For instance, a solution to this could be to include 2 grams, so 2 words, tokens of 2 words, And in this case, not will be in every cases before the word of interest, the verb. But this is a great point. So that's why we should be careful when preparing our text for analysis. Okay, and we were in lemmatization, yes. So yes, as I said, we have different form of a word and they have the same meaning. So we have that we want to have the same token for this word. And one method for lemmatization is called stemming. Stemming is like you remove the end, the suffix of the words. So for instance, connection, we will remove the yon at the end to make it connect, so that every connection, connecting, connected words are become connected. Yes, because they have the same meaning. And there is an attribute in spicy which is called lemma, and this makes the job for us. So for instance, if we have the sentence, so the tokens runs, run, running, runner, runners, the tokens, the lemma for each words are run for run, run, and then runner. So it makes a difference between runner and run, but for different form of the verb, it doesn't make a difference. So, and we see here that it goes beyond than only stemming, because it transformed the past form of the word into the present one, and this is useful in many cases. Okay. Any question on this? All right. Next is entity detection. This is useful in some cases. So what is this? This assign, this identifies important elements in a text. For instance, person, date, locations. Yes, so we have this ends attributes from Spacey and the label of the entity. So if we run this, we will have, for instance, I have a text from an article, and we can see, for instance, that Donald Trump is an entity in the person. This is a person. Twitter is an organization. US is a location. Late January is dates. That month alone is a date, and so on and so forth. So entity detection is useful here to recognize, to detect entity in a text, and this may be useful for application, for classification, for instance. Okay, and we can also using this Placey, we can also show this in a more beautiful way, so with colors, and so we have our text with the colors. For instance, purple is for person, and this color like white blue is for dates. Okay. So it could be useful for some applications. Okay, any question on entity detection? Yes, this is, we have in spaCy, we have, so I'm answering the question from Anna, what is the e.i.label in your list comprehension? So we have two of them, and the first one with this underline character is always the, how to say, the name of the class or the name of the, yeah, the attributes. And the second one is like a number, the number of the attribute, because we always have to have in mind that we then want to use it in algorithm. So if we have a number, this will be then useful. For instance, if you want to use this entity detection in an algorithm, then we can use these numbers to as inputs in the algorithm. And this is the same for like just here lemma. I can also, for instance, we have also the lemma without the underline character, and this is also like a number, and this is the same for the same label. So this is used for then for yeah, if you want to use an algorithm with it. Okay, it's clear now. Okay, so let's do an exercise. So we have a sentence and we want to print its lemma for each word. So I let you like, yeah, 2 minutes. This should be 2-3 minutes. And then I will correct this. So at 57, I will correct this. And yeah, or I let you like 5 minutes. At 5, I will correct both exercises. Like the first one is to print the lemma of each word, and the second one is to create two lists, so to split the sentence according to punctuation, like as we did before, and the words. Okay, so 5 minutes, and then I do this. And if you have, yeah, okay, and if you're done, you can write down in the chat, and if there is a lot of time, then I can go and correct this. Okay, 5 minutes. This shouldn't be so difficult. Okay, has someone an answer to the first question? Nobody? Okay, there's someone. Okay, you create spacey object and then, yes, that's, yeah. So both answers seem to be correct. So the first step with spacey is to create a spacey object, so spacey document. So we create from the sentence, we create a spacey object, and then can add some code, and then quite easy. Now that it's a spacey object, we can like for each word in the document, we want to print. We can print its text, and we can also print its lemma. And we use this one because we want to see how the lemma, not the number. So we want to see which lemma it is, not the number. And if we do this, we see that, for instance, so it make the t lowercase in this first example. Then your is a pronoun, so it did this. We will see this later also. So with all pronoun, it makes the pronoun like your, you also. So this pronoun class for the pronoun, and for instance, depends with s is like without s now the lemma. So yeah, and so on and so forth. So like the same for plural form, it makes singular, and yeah, and so on and so forth. So, and for the second one, we want to create two lists. The first one with the punctuation, the second one with the words. Yeah, we can filter also the space, you're right. The spaces. Aliu, you're right. Does anyone has an answer for the second one? Okay, I can correct this one. So we want to create two lists. So the first one is the, we can say this is tokens. We create two lists, and then the punctuation, for instance. And then we can do, for instance, we can also do the spaces, but this is not, yeah, we can remove them and not make them in the list. And then for words in doc, if the word is punct, we can use this is punct. If it's true, then we add the word to the punctuation lists. And what can we do, for instance? We can do something like, yeah, if you want to remove the spaces, we can remove them, but we can also do like easily like this. else tokens happens word. And we can also make the spaces in the first with the space. So if it's punctuation or space, we add it to punctuation, and else we add this to the tokens. And if we then print the punctuation, then we have all punctuations, so like double points, the spaces, and the points, and so on and so forth. And then if we print the tokens, this should give us all tokens, all words. Okay. Any question on the small exercises? Okay. This was not so difficult, I guess. Okay, so, and any question on anything we saw so far? Because now we turn to text representation, and the rest should be clear if you want to understand this one. Okay, fine. So now we can go through text representation. As I said before, there are two ways to do this. The first one is the bag of words, and we use the count vectorizer class of scikit-learn. And the second one is this TF-IDF. I think Professor Vlachos didn't say anything about this, but because we will use this in the text classification, I will cover this one. This is not so difficult, and this is very powerful. But first, so the goal of this is to make to transform a text into numbers to make it usable for an algorithm. And for instance, we have those 3 sentences. So with about Donald Trump, and we make a list of them, and then we can transform. So let's do this. The first one, bag of word, is basically you make an array of all words that appear in all sentences, and then if the word is in the sentence, for instance, Donald is in all 3 sentences, you give a 1, and if it's not, you have a 0. So we use the count vectorizer, and in this case, we want to have n-gram, this parameter here. We want to have n-gram of either 1 words or 2 words, because we have an n-gram range of 1 to 2. And we also specify the stop words of the English language. So this remove automatically the stop words. Okay, then we fit transform our texts, and we make an array of it. So this yields something like this. And if you want to show this and understand this in a better way, we can make a data frame of it. So these are the features. For instance, so we saw that we have 1 gram and 2 grams. Because, for instance, we have the word American and also American trading, attack American. So they are, I guess, in the first for instance, attack American is like here, and so on and so forth. So attack, where is this? The second was American trading. Where is it? I cannot see this. Yes, American trading. This is this 2 gram, for instance. So we have both 1 gram and 2 grams, and we can represent this as a data frame where we see it, for example, that American is only in the first sentence, but Donald is in the 3 sentences. Donald Trump also, and so on and so forth. So, for instance, Trump is is twice in the third sentence. So we give the occurrence of each word in the sentences. So if you have a large texts to analyze, you can imagine that there is a lot of zero in such data frame, but this doesn't matter because the algorithm can learn on this. Okay. Any question on this bag of words method to transform words into numbers? Words in a text into numbers. Okay, and the second one, this TF IDF is basically the same. You want to transform texts into number, but you do a multiplication, TF times IDF for each word, and this shows the importance of a word both in the document, like here, for instance, if a word appear more than once, it would give a 2, for instance here, Trump, but also in all texts in all instances. So for instance, so a word that appear a lot of time in one text, but very few time in the other texts will have a high value. And a word that appear in all texts will have a lower value. For instance, we will see this, but for instance, actually I can do this. So for instance, in here I put the texts. So for instance, we see that where is it? Trump, Donald, for instance. Donald has a lower value here than the other one because it appears also in the other texts. So this TF, IDF, the important thing to remember is that it is a multiplication. So TF is like how many times the word appears in one specific document, and IDF is how many times it appears in the whole texts. And we are looking for words that appear in one document, but not in the other, so that the algorithm can better classify and learn on this. For instance, this is the same for Trump. So we see that it appears 2 times in the third sentence, so twice, and we have a higher value, and those values are lower first because they appear less, they appear only 1, ones and also lower than those ones because they also appear in the other documents. So if you want to use this word trump to classify the document, you are not so, you won't be able to do this because trump is in all three sentences or documents. So is this clear? Because this is important, even if the prof didn't talk about this, but if you do your project on this. Okay, any question on bag of words, TF, IDF, on anything else? Okay, nobody. So there is one exercise, we can do this. And then we can turn to the example with the classification of reviews. Okay, so the exercise is to create a TF IDF representation of the three above sentences, but this time using bigrams, bigrams, and the following stop words. So you have like, I give you like 2 minutes to do this, and then I will correct this. Okay, there is a question. I don't understand it well. How is the n-gram taken into account in TF IDF? Can you specify your question? So we have the class basically, and okay, the question, the results seem to show only one word, not group of words. Yes, because I specified the n-gram range here of 1, in this case. I forgot to say this. So in this case, I have 1, and basically what if you want bigram, I don't know how to say this, you may want to change this if you see the documentation, but this is you can understand this quite easily. 2.2 if you want big RAM, and English, it is specified in the documentation. Here, that you can pass a list of stop words. So we can do this. So instead of English, you want to have this list. So you simply write the list of stop words. Normally you won't do this, but for the example, you do this. And then this is basically the same. So if we try to do this, we have our token of 2 words with the frequency. And for instance, as before, Donald Trump is lower because it appears in all 3 documents and is not so useful to recognize one text, to classify one text. Okay. So that's it for the text representation, sorry. And we can now do a real life or real example. So we have a data set, I will talk about it later, but basically, yes, we need additional packages. We will use a pipeline. I will show this later, the stop words, train test splits. We will use also logistic regression for the classification and the matrix, so confusion matrix, accuracy score. So, and let's talk about the data set. So we have reviews with rating 1 to 5, dates, the variation of the product. So it's about Alexa. So the variation, and then what's of interest. So the review. So fun so far, learning to use her, and setup is so easy. And you see, for instance, the feedback is always, in this case, always positive. The feedback is 1 for positive, is 0 for negative. So for instance, works great and simple to set up is positive. And I don't have any negative example, but if I do this again, and maybe it can give me a negative example, because basically we will see the data set is unbalanced. There are way more positive. Yes, for instance, yeah, I didn't order it. This is negative. Okay. And we want to, based on the text, to predict the feedback. So whether this is 1 or 0, positive or negative. So we have those 5 columns. We want to change the dates into datetime. This is not so useful. And if we count the value of feedback, so positive or negative, we see that the data set is unbalanced. So we have almost 3,000, almost 10 times more than 10 times more positive reviews than negative ones. So this should be a very good product. Yes. So the data set is unbalanced. This is important for the following to remember. So if we compute the base rate, so this means the probability of the most common class, so the positive class, the base rate is in this case then really high, like 91%. This means that if we classify every new instances into the positive category, we will have an accuracy of 91%. So we have to bid this. This will not be easy. Okay. So first step is to create a tokenizer function. And for this, we want to remove the punctuation marks. So we have the punctuation mark here. We have a list of them. We also need the list of stop words. We use the one from Spacey, like this. And we load the English language model as before, and we define a function that we will use to tokenize a sentence. So we first create a Spacey object, then we lemmatize and we convert into lowercase. So we take the lemma and lower it. And then we remove the stop words and the punctuation. And there is also this pronoun category. This is explained here. This is how Spacey handles the me, I, they, it or he, and it normalizes everything as a pronoun for the algorithm. And exactly, and it returns my tokens. So if we take an example, so a sample of review, for instance, this one extremely easy to use, switched away from direct TV and use it to stream TV. If I use my function on this review, this gives me like this one. So it remove the two stop words. It make the switch with a lowercase, and so it tokenized my sentence into words. This is the first step, and we can do what we want here to tokenize. That's my choice. Okay. And the second step is to define the vectorization. So to turn those words into numbers, and we use a vectorizer, and we defined the tokenizer. We use the tokenizer we defined just above to make the transformation. So in the class, you can specify a tokenizer. In the class, tokenizer should be somewhere here. I don't see it. Tokenizer here. So the default value is none, but we can specify one, and that's what we do in this case. So our tokenizer, so it means that we will do those transformation before applying the TF-IDF algorithm that we saw earlier. And then we can use logistic regression to classify the reviews. So we want the verified reviews as X, and the Y is the feedback, +1 or -0. And we do as always, we split between train and test sets. This gives us a train set and the feedback, and we define the classifier, and then we can define a pipeline. A pipeline means some steps that we want to do for the model. So we first want to vectorize, so to transform the text into numbers, and then to use logistic regression or classifier to do the analysis, the classification. So we fit the model with the pipe we just created on the training set, of course, and this gives this takes a bit of time. So we have our model that is fitted, but the pipeline is like we have the first step, we vectorize, as I said earlier, and then we classify. So we do it all in one step using this pipeline. This is very useful instead of first vectorizing then classifying. And then we want to evaluate the model like last time. So we evaluate the model and we compute prediction for the test sets and we evaluate it. Using the function we defined. And we can see that the accuracy is like 92. The base rate was 91.8, and the difference is that it classified everything as positive and only 2 as negative, so it doesn't work very well in this case. And this may be due to a lack of negative reviews, so that the algorithm don't learn to classify negative review well because there are too few of them. So we did better than the base rate, but only 2 out of like 600 something, which is not a lot, but we did better. And we can do the same on the training set. I will already launch this such that we don't lose so much time. Exactly. So any question on this? Okay. And if we do the same on the training set, we can see an accuracy of, again, 92. So only 6 out of 2,500 have been classified as negative. And this may be due, as I said, to few examples of negative reviews for the classification. So it classifies basically almost everything as positive. And if we look at the 2 instances that are classified as negative, we have, for instance, the word return and stop for those ones. And for the negative in the training set, what do we have? Okay, we have something like, so it makes sense. I've already returned it is negative, and it worked for a month or so, and then it stopped. I can read this, but it also looks like negative, and we also see in the training set that there is this word stop. So what it did, basically the algorithm only learned to classify the word return and stopped. And then it classified the 2 instances here because they have those words. So I have also the word return here. But this is better than classifying everything as positive because we recognize for 2. And we can also illustrate this with a prediction for new reviews. I have 1 positive, so I really love the product. It is very helpful. I use it every day. And then one negative with the words that the algorithm figured out to classify as negative, so stopped and return. And then something negative but without those words. And if we predict with this example, we can see that it predicts 1, 0, 1. So it predicts positive, for the first negative with those words 0, which is then a good prediction, and for the second one positive, which is a mistake. Okay, any question on this? And the last section is how can we improve this? So because this is not so, yeah, we did something two reviews, but this is not so, this is as if the model, yeah, does not work very well, and we want to improve this, and there are some ways to do this. We will see. This is the topic. One of those is the topic of the second one is the topic of the next week or the week after, because you have this block section. So the first one, we can, for instance, resample the data. We can add negative example in order that so that the algorithm can better train and learn what is negative. We can also try to tune the hyperparameters of the model. This means, for instance, having another stop words list, having another algorithm to vectorize the words, to tokenize using n-grams, so 2 grams, 3 grams, and so on and so forth. So to tune those parameters, we can also, and this is also, yeah, we can also improve text preparation. Yeah, this is basically the same as tune the hyperparameter of the model of this vectorizer. So we can also, for instance, add the entity recognition in the model, some stuff like this. And we can also use another classifier. And I illustrate those ones below. So the first one, we can improve the text preparation. So we tune the hyperparameters of this class. For instance, if I want to, we can basically want to try to fit a model for each parameters combination, and I chose 4 of them. So the n-gram range that I can modify here, this min df, max df, and the analyzer, if you do the analysis on words or characters. And the first step is to like define your config, and then to create a list of config using like for loops. And we have our different configurations. And then we can fit the model for each configuration. We want to fit the model and print the config and the accuracy, so to evaluate the model. And then we may choose the model that has the better accuracy. And I already did this because this takes a bit of time, and this is not so, this doesn't bring much, but this is like for illustration purpose. So the first model is the same system with 1 grams. Then with characters, it doesn't work at all. So it classifies everything as positive. Then with 1 gram and 2 grams, 2 gram and words, it doesn't work, and so on and so forth. So not so helpful in this case, but this should be very helpful to tune such parameters and to see the accuracy score, how it evolves. Okay. So any question on this? And I have 5 minutes remaining for. Okay, and for resampling, for instance, in this case, I remove some because I don't have any negative reviews to add. So I remove some positive reviews such that I have a base rate of 0.5. And in this case, I only have done 500 rows. And in this case, the base rate is then 0.5 because I have the same, I take a sample of the positive reviews, which is of the length of the sample of the negative one, and then I concate both. And in this case, I have a precision of 88. You may have another one because the sample is not the same. Because your sample is not the same, this function takes random, but like it's better, and it figured out to classify reviews in the negative category. So we learned to do this, and this may be, even if we only have 80% something accuracy, this is better than the base rate of 50%, but this is worse as before, like 92, but this may be more useful because the model really learned to classify negative reviews in this case, because we have a balanced sample. So with approximately the same number of positive and negative, in this case exactly the same, but this is for illustration purpose. So it's good. It is good to avoid to have too much from one class over the other. Okay, any question on this? Okay, and if you don't have any question, last but not least, I use another classifier, random forest. So basically this is the same, but I change only, instead of logistic regression, I use another one, another classifier. I don't have the time to explain this, but basically this is a decision tree. We will see this in one class during one class in the future. This is the average of many decision trees, this random forest. So this is a forest, and it gives better results in this case. So we may use those three methods, techniques to improve the accuracy. So use the best classifier, resample, and also then to tune the hyperparameters of the model. And you can also, you can both tune the hyperparameter of the way you vectorize your data, so this TF IDF, and you can also tune the upper parameter of your classifier, so the logistic regression, or in this case the random forest, which I didn't do here, but you can also naturally of course do this. And in this case, instead of 2 we have 10, which is a bit better, but not much better. We have 10 negative reviews that are correctly classified in this case, and in the training set we have almost an accuracy of 1, and in this case you may ask yourself, maybe this is overfitting. You should be careful. If it's 90 something, 99 something, it should be, this could be overfitting. Okay, any question on this lab session? And I have a bonus when where I try to predict the rating. You can look at it on your own. This is not so long. I try to predict the rating. So we have a multi-class problem. We try to predict the rating from 1 to 5, and you will see that the random forest is also better than the logistic regression for such problems. Okay, any question? No question? Yes, I will share the solutions for the lab from last week. I will try to find it. Okay, then thank you for attending the lab session. I hope this was useful, and I see you in 2 weeks, I guess, or maybe later, because the next time maybe Ahmad will do this. Okay, if you have any question, it's now. Otherwise, have a nice week, have a good week too, and thank you for your feedback. What's the block week? I don't really know what's the block week. We didn't have it as I was in the first year master, and I didn't do the master in information system. I don't know if it's only for your master or for everybody. I don't know. I don't know what's the block week. But I know that there is no lab session and no class.